Welcome back to this lecture series on pulse width modulation for power electronic converters. We have done 32 lectures so far. This is the 33rd lecture today on this in this lecture series. So, we have done several of these modules as you have already seen. There are about 8, 5, 9 of these modules have been completed, and we are now in the 10th module. So, the earlier modules this module first focused on the topology for DC-DC and DC-AC converters, and the second module focused on the few applications of voltage source converters. Third module focused on certain fundamentals and basic principles pertaining to pulse width modulation, and the fourth module focused on generation of PWM at low frequencies. The fifth and sixth modules focused on generation of PWM waveforms at higher switching frequencies, when the inverter is switching at frequencies much higher than the fundamental frequency desired. So, there are two different approaches, one is triangle comparison and the other one is space vector based PWM. As I have said many times before, whatever is possible with space triangle comparison based is possible with space vector, but it is not possible wise. There are certain space vector based PWM methods which cannot be implemented as triangle comparison methods. So, space vector based PWM is more general than triangle comparison PWM methods, but triangle comparison PWM methods could actually be easier to implement. So, we have seen many of these. So, there are continuous and discontinuous bus clamping PWM methods, or discontinuous PWM, also we call it as bus clamping PWM. These continuous and discontinuous PWM methods can either be implemented as triangle comparison methods or as space vector methods. Many times it might be easier to implement them as triangle comparison methods, but there are certain PWM methods called advanced bus clamping PWM methods. So, they rely on certain flexibilities offered by the space vector based PWM. The triangle comparison based PWM is based on the flexibility that the null vector time, there is a null vector produced by the inverter, and that is applied using two different 0 states. So, the null vector time is divided between the two 0 states, and there is a degree of freedom there, or in other words there is addition of common mode voltage. Whereas, in space vector PWM you can have that division of null vector time between two 0 states, and also you have the freedom to apply an active state more than once. So, there is what you can call as division of active vector time also. So, there is certain additional degree of freedom available in the space vector based PWM method, which leads to what we call here as advanced bus clamping PWM methods. So, these advanced bus clamping PWM methods they result in bus clamping just as the discontinuous PWM methods do. So, a phase would not switch in some region of the fundamental, it would switch at the nominal frequency in certain other region, and it would switch at double the nominal switching frequency in some other regions. So, these are advanced bus clamping PWM methods. We discussed some advanced bus clamping PWM methods as part of our the space vector based PWM, and we did analysis of the PWM methods, continuous, discontinuous and advanced bus clamping PWM methods to a certain extent in this module on line current ripple. So, we showed that there are certain conditions where the advanced space vector based PWM could be better than the other methods, particularly in terms of line current ripple at high modulation indices. And we also showed that some advanced space vector PWM methods could actually be better in terms of torque ripple in this particular module. So, we also tried to evaluate the DC link current for various methods, and we showed that the DC link current, I mean the RMS value of DC link current is actually largely independent of the PWM methods that you really use now. So, after having covered these modules, we have been dealing with this module on evaluation of inverter loss. This is on account of the non-idealities in the switches. We are still not considering, I mean in the losses in the passives and all that, which you can easily find out. For example, if there is a filter inductor and there is an amount of current flowing through that, the filter inductor would have some resistance, internal resistance, let us call it R, and you can actually calculate the loss in this inductor using this with a knowledge of the RMS current through the inductor. Similarly, if there is a capacitor, here we were able to find the DC link current and the capacitor current. So, we can find out the RMS current, capacitor current. So, the RMS capacitor current and the equivalent series resistor of the capacitor can give us the loss in the capacitor. So, here our focus has been on the essentially the semiconductor devices in the inverter. So, there are two significant kind of losses, one on account of the forward conduction, so like which is called as the conduction loss, which is on account of the forward drop, and the other loss is on account of switching. So, when there is a switching transition, there is a certain amount of power dissipation, there is some amount of energy loss. So, in the first lecture in this module we focused on the conduction loss, and the second lecture we focused on switching loss. Today we also found that the PWM methods the variation of the conduction loss with PWM is not too high. So, because always either a transistor or another diode conducts, so that there is some influence, but it is not too high, whereas the influence of the PWM method on the switching loss is very high, particularly for the discontinuous PWM methods, not for the continuous PWM methods, but for discontinuous PWM or bus clamping methods, and also for advanced bus clamping PWM methods. So, that is something we discussed in the last lecture. So, today we might get a clearer idea of this effect of the PWM methods on switching loss, and we would also actually try and design some PWM methods which would reduce the switching loss compared to standard methods such as conventional space vector PWM. So, that is what we will be doing in today's thing, that is in the present module, in the last lecture of this module, and in the subsequent modules we will focus on the inverter dead time, its effect on over modulation and PWM for multi-level inverter. So, as I just said before, we covered all these aspects in the previous lectures, that there are ideal switches, there are real switches. Real switches have forward drop, and therefore, there is some finite amount of conduction loss, and we tried evaluating this various conduction loss for the different PWM methods. We discussed how to evaluate the conduction loss for the different PWM methods, and we discussed the turn on and turn off energy loss, and we tried to evaluate the switching loss for different PWM methods, how to go about switching. So, today what we will do is, this was based on the turn on and turn off energy loss, which is a function of the operating conditions. For example, if a device is turning on and there is certain amount of DC bus voltage, there is certain amount of current that it has to conduct, and it is operating at some temperature. So, all this would decide on how much is the turn on energy loss. Today what we would do is, we would simplify that. Basically, we would simplify that turn on energy loss and the turn off energy loss, we would relate them more directly to the current that is being switched. So, and with that simplification we could actually do a comparative evaluation of different PWM methods more conveniently and easily, and then we would use that idea to design PWM methods which can actually reduce the switching loss. Okay. So, this is what is going to be the focus for today's lecture. So, we call this as design of PWM for reduced switching loss in 3-phase inverter. Alright. Now, let us get started. This is the 3-phase inverter, this is a 3-phase load which is not known, it is not shown here in the figure. There is this DC side, and there are losses in these devices, both the transistor and IGBT, etc. We have this now, and there are conduction and there are also switching losses. The present focus is really on the switching loss. Okay. So, as we said, the ideal switches will not have any forward drop, and therefore no conduction loss, there is 0 leakage current, therefore no off state loss, and they turn on or turn off in an instantaneous fashion. There is no energy loss during switching transitions. That is about the ideal switches. What about the practical switches? They have finite forward drop, therefore there is certain amount of conduction loss, and there is negligible leakage current, and therefore the off state loss is also negligible, we do not have to worry about that. So, what we need to worry about is mainly the conduction loss during the on state and the losses during the transitions, switching transitions, because the turn on transition and the turn off transition times are finite, and there is significant amount of energy loss during these transitions. So, we evaluate conduction loss and switching loss, etc., and today we are hoping to design PWM methods which would reduce the inverter switching loss significantly compared to something like sine triangle PWM or conventional space vector PWM. Alright, I would emphasize the fact that there is a reduction in switching loss, not really conduction loss, but it has been shown that some of these methods result in an overall, the conduction loss slightly changes, maybe increases or decreases, but with some of these methods the reduction in switching loss is so significant that there is also a reduction in the total semiconductor device loss. So, which has been discussed in some papers, whose reference also I will give you towards the end of this lecture. Alright. So, now why there is a loss, as I was saying, it is not instantaneous. You can see that the voltage takes so long to fall and the current takes so long to build up. The trouble is the current builds up faster and ahead of the voltage falling down, and therefore both voltage and current are high concurrently during this interval, and therefore there is a significant amount of power loss, there is power dissipation is very high. So, it could be as high as the rated voltage multiplied by the rated current, it could be so high. There is instantaneous dissipation, and you need to integrate this dissipation over this interval, switching interval time, and that will give you the energy lost in this transition now. And similarly, you have the turn off transition, and we found that the same kind of story here, the current falls, and before the current starts falling the voltage is risen across the device is risen. So, there is a significant amount of loss now. So, there is this energy loss, turn on energy loss E on, this turn on of energy loss E off. These are available as functions of DC voltage, current and junction temperature. This is normally they are available in the data sheets. Similarly, the diode has what is called as a reverse recovery in energy loss. So, there is a reverse recovery process, there is some energy loss associated with that. So, you can find out how much is the energy lost at a particular operating condition, and then you can look at how many times it is turning on or turning off. So, you will know that the power loss can actually be calculated, alright. So, this is largely from data sheets. So, we also saw yesterday on some possible references where I mean the last class where we could actually look at a few there were a few papers which dealt with how you could actually evaluate E on and E off, how you can actually measure the switching characteristic and you actually evaluate your E on and E off. I am not going to repeat them today, right. So, now what we are trying to do is that E on and E off business which may be available in the data sheet or which is which can be produced like experimentally you can evaluate under certain conditions. We are trying to simplify that today to have a simplified analysis. So, that is our primary idea. So, and this is also mainly for comparative evaluation of PWM methods. So, one of the assumptions is that there is this voltage source inverter, this is driving some load, some RL load or induction motor load, and around over the line cycle the DC voltage cannot be expected to be constant, because sometimes the current is higher, sometimes it is lower, and the DC link current itself it keeps changing. It's not a fixed current, it's a time varying current, and there is all this load side inductances and all that. The DC bus voltage is not expected to be a constant, really speaking. There will be certain amount of ripple on the DC bus voltage, like 300 hertz ripple for example, because the DC bus voltage is also established by a rectifier which is supplying this inverter. So, you will have that. Now, one simplifying assumption we are first doing is we are saying that the DC bus voltage is constant, we are ignoring variations on that. This is something which we did yesterday also. Then change in the device transition times with load current is ignored. So, there is when the current, that is a simplifying assumption, that is what happens is let us say there is R phase leg, sometimes it is switching a low current, sometimes it is switching a high current in one direction or in the other direction, alright. So, when the current is low and when the current is high, the device transition times are supposed to be different. It's there may be device rise time, like the current might take about 250 nanosecond to rise from 10% to 90% of its final value, and that may be 250 nanoseconds at some value of current, it could be 275 nanoseconds at some other value of current, and maybe 300 nanoseconds at some other value of current. So, what I am trying to say is those device transitions we are first trying to ignore for the purpose of simplicity. So, we are ignoring those changes in device transition times with load current switched. For example, the rise time of the device at 10 amperes and the rise time of the device at let us say 50 amperes would be different, that difference is being ignored. Then there is E on and E off. So, they depend on a number of things. We are taking them to be proportional to the load current, whatever is the current being switched, we are saying E on and E off are proportional to that. And this load current itself has a fundamental component and harmonic components. The sum of all the harmonic components is ripple. We say that the harmonics are all negligible. The inverter is switching at reasonably high switching frequency and the load has good filtering characteristics. So, like higher frequency voltages are filtered better by inductive loads, RL loads or induction motor load, and we will ignore the ripple, all the harmonics of the load current. Therefore, what we are going to say is the switching energy loss is proportional to the fundamental phase current. If you want to say switching energy loss in a particular leg, let us say R phase leg, is proportional to the fundamental component of R phase current. That is the simplifying assumption we are doing today. Once you have that, it is easy for you to evaluate. So, it is directly, this energy loss is directly proportional to current. So, getting its average value over a half cycle of the current waveform is very simple, because this E on E off and E on plus E off, they are also sinusoidal functions. So, you can very easily evaluate its average and you can come up with the power lost. So, it is easy to do this now. So, this is easy for us to do a comparative evaluation of these various PWM techniques and in terms of switching loss. So, when you want to compare two different PWM methods, these simplifying assumptions make it really easy for you to do this. So, that will certainly be helpful for us in designing new PWM methods. So, let us start off with the sine triangle PWM. 3 phase sinusoidal signals are there. So, this is for R phase, Y phase and B phase, and you compare them with a high frequency triangular carrier and feed them to the inverter. So, what happens? There is a certain amount of AC voltage that is applied. As I said, that depends on the modulation index. Here it is 0.8 times the peak of the triangular carrier. The triangular carrier is not shown, but it is considered to have a positive peak of +1 and negative peak of -1. So, this modulation index is 0.8. So, the peak phase fundamental voltage is 0.8 into VDC by 2. So, if your VDC is 600 volts, VDC by 2 is 300, 0.8 into 300 is 240 volts. So, 240 volts is the fundamental phase to neutral voltage applied on the load. So, and depending on the load impedance, there will be a corresponding current, fundamental load impedance now. So, let us say this is the load current. So, there is a certain amount of current, and we saw that there is switching energy lost. Now, what is our simplifying assumption? We have simplified that the loss is proportional to the current that is being switched. So, we say that if the current being switched is 0, the loss is also 0. So, if the current being switched is so much, again here. So, let us say how would the variation, how would this loss vary, the switching energy loss? It would vary in the same fashion as the current varies. So, let us say it is like this only. So, let us say this is our switching energy loss. Switching energy loss is that the current 0 here, I am sorry, this is the current 0, it comes down like this. So, further what happens? It goes up the same way. Like this. This is your switching energy lost. And what is its average value? It is rectified sinusoid. So, you can always say it is 2 by pi times its peak value. So, it is fairly simple to evaluate the average value here now. And the significant thing that you can note down is, now let us say the current waveform is having the same amplitude, but a different power factor. Now, the current waveform may be at a different phase angle. Here it is shown at 45° lag. It may be, let us say, 30° lag or whatever lag. So, what is going to happen is your ESW is going to be similar to that. That is, the wave shape is same as the rectified current, the fundamental current rectified. It is only going to have a phase shift, but it does not matter, the average value will continue to be the same. On the other hand, if the current amplitude increases, for example, if the current amplitude doubles, the corresponding switching energy loss peak value will also double. Therefore, the average loss will double. But when the current amplitude is same, is given as some 0.6 per unit here, if it is the same, but if the power factor changes, then the whole thing is not going to change. I mean, the switching is not going to change. Thus, for any particular sine triangle PWM or any continuous PWM, the switching loss does not vary with power factor, as we already discussed yesterday. So, that is not only sine triangle PWM, that is true about other PWM schemes also, because your energy switching loss is dependent on the current, that is all, there is nothing otherwise. It is not exactly dependent on the duty ratio. The only exception is the duty ratio is 1 or 0. In that case, a phase will not switch at all. If phase does not switch at all, there is no switching loss. So, as long as a phase switches, it may be 0.1 duty ratio or 0.9 duty ratio or whatever, the switching energy that is lost is proportional to the current, and therefore, this is the kind of wave shape that you are going to have, and its average value is going to be whatever it is. Therefore, the switching energy loss depends upon the amplitude of the load current. It is independent of the load power factor for continuous PWM methods, and it does not change significantly from one continuous PWM method, say sine triangle PWM, to another continuous PWM method, say third harmonic injection or conventional space vector PWM method, right. Now, you have this fundamental current, now you have this one. So, this is the point that I was already trying to do, fundamental current, and let us say this is your I mean at a different power factor. The first is your modulating signal, this is at a different power factor. So, you would have this here, I am sorry, ignore this point. So, it starts going up here. So, you have it like this. So, you can see that it is just a phase shifted version of what you got earlier. So, the average value is just the same. So, you have certain average value which would still be the same here. Alright. So, when this also, this is an example of third harmonic injection. So, like another continuous PWM method. Why do you say continuous PWM method? You look at the modulating signal. The modulating signal is a continuous function of time. or the fundamental angle. So, and all the phases are switching, all 3 phases are switching, there is no phase which is clamped here, alright. So, the losses are same now. So, this is true about conventional space vector PWM also. So, in conventional space vector PWM, if this is your fundamental sinusoidal modulating signal, and this would be the kind of common mode added, and you would get a modulating signal which is like this. It is also here also the switching loss is same as we discussed before. Now, just to summarize or whatever or recap, can be modulating signal can be continuous or discontinuous, and the switching loss does not vary significantly from one continuous to another continuous PWM scheme, whereas it varies significantly from one discontinuous PWM to another, as we saw some examples yesterday. And so, now whatever we want to do, like designing PWM schemes, obviously these are not going to be continuous PWM schemes, because the continuous PWM schemes do not influence the switching loss at all. We are going to focus on the discontinuous PWM methods first, or the bus clamping PWM methods first, and then the advanced bus clamping PWM methods next, to be able to reduce the inverter switching loss. That is what we are going to do today. So, in bus clamping, why does it affect? Because a phase is clamped, one of the DC buses in certain intervals. So, and where it depends on the modulating signal. The modulating signal is a discontinuous function of time. There are several possible modulating signals. So, one modulating signal may clamp a phase between 60 to 120 degree of fundamental angle, another may clamp it between 45 degree and 105 degree of that, and so many different modulating signals are there. Depending on the modulating signal, a phase would be clamped over some interval or another interval now. So, whenever a phase is clamped, there is no energy is lost. So, this has been one of the interesting things about bus clamping PWM. That is also one of the reasons why they are being studied or being used. So, there is certain amount of energy is saved, but the energy is saved by not switching a phase is highest if the phase is not switched when its current is close to the peak. On the other hand, if a particular phase current is going through 0, is very close to 0 in a particular carrier cycle, and if you clamp that phase, the energy saving is very insignificant. So, these are certain things we discussed. So, switching loss PWM, switching loss is, it depends strongly on the kind of modulating signal you use. So, when you are using bus clamping PWM, from one PWM to another it will vary, and also from one power factor to another power factor it will vary now. So, the point is, now for a given power factor you will have to know what is the right kind of modulating signal that will minimize. So, that is what we need to do. We can start looking at some examples. For example, we will look at unity power factor and we will see what is best, and certain examples of power factors, and then we will try to go about generalizing it in some sense. So, one thing we will do is we will define certain normalized switching energy loss. Our purpose is comparative study of PWM methods. So, the PWM all we are considering a case where the same operating condition of the inverter, maybe PWM1 or PWM2 or PWM3 is being used. So, the same operating conditions. So, the energy loss in R phase leg, we are saying that that is a normalized energy loss is proportional to the unsigned value of IR1, right, because it may be plus 10 ampere or minus 10 ampere, the energy lost is same. So, this is IR1, the unsigned value, absolute value of IR1 divided by IM, where IM is the peak value of the current, and so this is the unsigned value of sin omega t minus phi, where phi is your power factor angle. So, here I have used minus phi, in some other places I have used plus phi, but please do not mind that. So, you know what I am trying to say. So, this is certain power factor angle, this is phi here. So, EY similarly you have, because this is sin omega t is your R phase modulating signal, Y phase modulating signal would have like amplitude multiplied by sin of omega t minus 120. So, the sin of omega t minus 120 is the phase angle for the Y phase fundamental voltage. So, omega t minus 120 minus phi would be the phase angle of the fundamental current of Y phase. So, this unsigned value of sin omega t minus 120 plus phi is the energy that is lost in the Y phase. So, there is approximation, we have simplified today, and so this is what it is now. Again, the normalized energy loss in B phase can be given by sin of omega t plus 120 minus phi, its unsigned value. So, these are the losses in individual legs, the normalized switching energy losses in each leg. So, you can add up all the 3 as EE bar, EY and EB, alright. So, if you are going to discontinuous PWM, why were we adding up here? Because all the 3 phases switch in a continuous PWM. Therefore, certain amount of energy is lost in all the 3. So, the total amount of energy lost is the sum of all the 3. Whereas, if we go to discontinuous PWM, maybe R won't switch or Y won't switch or B won't switch in a particular carrier cycle. So, it may be ER plus EY or EY plus EB or EB plus ER. Let us look at it now. So, in the discontinuous PWM, you are adding a common mode signal which results in bus clamping. So, there are two possible common mode signals. One we call as the positive common mode signal, that is, from the carrier positive peak we subtract the M max, the maximum one of the 3 modulating signals, and we get this now. Similarly, the carrier has a negative peak minus V peak, or which is called as minus 1. The most negative of the 3 sinusoidal signals is subtracted from that, and you get this what we call as the negative clamping common mode signal now. So, if you add the red one to the 3 phase signals, it will result in the clamping of one of the phases to the positive bus. Which phase? That depends on which angle you are at. Again, if you add this signal to the 3 phases, it will result in clamping of one of the phase to the negative bus. Okay. Which one? The phase which has the most negative fundamental voltage, that will get clamped here. So, what we do is we follow this for 60 degrees and follow this for another 60 degrees, and we do it in an alternative fashion as we discussed this before. And if we follow these conditions, we can make sure that we can ensure bus clamping with equal loading with power dissipation in all the 6 devices being equal. So, if you are operating an inverter, you have to make sure that the same amount of power is being dissipated in all the 3 legs, and even in each leg the top device and the bottom device should also have the same amount of power dissipation. That can be ensured if you go through all these things, and particularly that it must have 0 average value, and so you can do this now. So, subject to these conditions, many bus clamping PWM methods are possible. So, what happens in bus clamping PWM? If you look at R phase, you will have an R phase switching energy loss, which normalized R phase switching energy loss, as we discussed before. This is simply proportional to IR, right. Similarly, this is the Y phase switching energy loss, this is B phase switching energy loss, but whether the phase switches or not is a question. So, what we can actually do is multiply this by what we call as a local switching frequency, that is, it may be switching or it may not be switching, and that local switching frequency is again normalized with respect to the switching frequency of the conventional space vector PWM or sine triangle PWM equivalently. So, this is energy, this is normalized energy, we are multiplying by switching by a frequency to get power. Of course, all of them are normalized here now. So, the same way EY can be multiplied by the same factor to get what you call as the switching loss. This is the power loss in the Y phase leg, and this is local. What we mean by local is this will vary with omega t. As omega t varies, this number will vary, because obviously this varies, and maybe this also would vary. Similarly, EB can be multiplied by this normalized switching frequency, normalized switching energy loss multiplied by normalized switching frequency to get the normalized power loss. Okay. Now, what about this ratio? When you are using a carrier frequency which is same as the conventional space vector PWM and the phase is switching, then FSW by Fs local is equal to 1, but the phase may not switch always, the phase may be clamped. If the phase is clamped, then FSW local is 0, FSW local by FSW conventional is 0. So, there is no power loss in that. For example, if R phase is clamped, then there is no power loss. So, here PSW R local will be 0, Y and B may be switching at the same carrier frequency as fundamental, then these will actually become, this is EY and this is EB essentially multiplied by 1. Now, so this is when it is clamped, and when it is not clamped it should be 1. Now, what is this 1.5? Yeah. So, what happens with bus clamping PWM is the average switching frequency is different from the carrier frequency. Let us say the carrier frequency is 3 kilohertz. What does a typical bus clamping PWM do? It clamps a phase for 60 degrees in the positive half cycle and 60 degrees in the negative half cycle. So, the device does not switch 300 cycles in a second. It does not switch all 300 cycles, though the carrier goes through 300 cycles in a second, individual devices do not switch. How many cycles do they switch in a second? It is only 2000. So, this switching frequency, but the switching frequency is not uniform everywhere. It is sometimes 3 kilohertz and sometimes it is 0. So, the switching frequency of a particular device, if you look at, is 3 kilohertz for 120 degree duration in a half cycle and 60 degree in another one. So, we can call the term average switching frequency. The average switching frequency is only 2 kilohertz now. The devices actually switch only 2000 times in a second, though the carrier frequency is 3 kilohertz. So, the average switching frequency is low. So, what happens? the switching frequency is reduced, the switching loss is also reduced, but sometimes the harmonic distortion might be affected. So, it is so sometimes what we do is to really increase the carrier frequency to 1.5 times. If you increase the carrier frequency to 1.5 times, now let us say conventional is switched at 3 kilohertz, whereas we are considering a bus clamping PWM which is switched at 4.5 kilohertz carrier frequency, then the average switching frequency with BC PWM will be equal to 3 kilohertz. So, sometimes it is fair to compare both of them at the same average switching frequency, which is the exact number of switching cycles every device switches in a line cycle or a second. Okay. So, actually if you increase the carrier frequency like this, then what you are doing is your device is switching at the same average switching frequency, but you will be able to achieve better harmonic distortion, lower harmonic distortion at high modulation indices. This is also a fact which we have studied and it has been widely reported in the literature. We also saw a few papers references which talk about this. So, what we do is sometimes we use the same carrier frequency as the conventional, or sometimes we use a higher carrier frequency, that is 1.5 times that of the conventional, and therefore, this FSW local will be either 1 or 1.5 depending on what the carrier frequency we have chosen is when the phase is switching, and when the phase is clamped it is only going to be 0. So, this way you can evaluate the normalized local switching loss for each leg, for R phase leg and Y phase leg and the B phase leg. Alright. So, now let us say take the specific example of 60-degree clamp. So, it is clamped for 60 degrees in the middle of every half cycle, and that is why we call it 60-degree clamp PWM. It is a nomenclature, some many papers might actually call it DPWM1 for example. Alright. So, this is the sinusoidal R phase sinusoidal signal, and this is the common mode signal, and the common mode signal has been added, and only you get this is the one now. So, R phase is clamped here and R phase is also clamped here now. Okay. So, if let us say we are talking of unity power factor, I have reproduced just the R phase fundamental modulating signal, this is the R phase actual modulating signal, and this is the common mode component, this is the current, this is the current. Now, what I have done is I have reproduced the current, I mean this is the fundamental current here. So, if this is the fundamental current, what is the loss going to be? The switching energy loss we have said is proportional to the current. So, we can say that this is the switching energy loss, this is the switching energy that has been lost. Now, here what happens? This is how the switching energy loss is, it follows here, this is in one half cycle. How about the middle duration? The switching energy loss is 0 because the phase is not actually switching at all. So, you have the switching energy loss like this. How about that? The same thing you will have in the other side also, the switching energy loss here will be 0 and it will go like this, it will come down, then here again will go back to 0. This is how the switching energy loss will be. If you are considering the same carrier frequency as the fundamental, then what happens? You actually save 50% of the switching loss, you save 50% of the switching loss. Now, what you might actually be doing is, this is the local switching loss now, if I consider the carrier frequency to be the same as the conventional. If the carrier frequency let us say is 1.5 times of the conventional, what will happen is this thing will get multiplied by 1.5. So, what is the number here? This is something like actually it is 0.6, this is 0.6 sin 60, 0.6 into 0.866, it is something little higher than 0.5. So, this will roughly go to 0.75. So, this would be the PSW local, this would be the PSW local for R phase at a higher carrier frequency. So, this will come down like this. So, alright. So, what has happened between here and here there is a difference now. Here it increases by 1.5 times. Why? Because it is being switched at a higher carrier frequency. Here it is also at a higher carrier frequency. Here also if you look at the average switching loss, you average this PSW local over a half cycle, you are going to get the actual what is switching loss. You will see that the switching loss is still about 33% lower than the original switching loss that you will have with the conventional space vector PWM. So, this is the best way of clamping. If you are having unity power factor load, the current also has its peak whenever the voltage has its peak. So, the best thing whatever you want to do is to clamp the phase around the peak of the current, which is same as clamping the phase around the peak of the voltage, and that is precisely what you are doing. So, 60 degree clamp PWM is the ideal answer to reducing switching loss when you are at unity power factor, when your load is at unity power factor. The problem is when the load is not at unity power factor, what happens? You need to change it a little bit. This is another particular case we are taking now. So, in this case if you see, the phase is getting clamped, but where is the current? The current is actually a little lower and here. So, here the current is high. It might have been advantageous if the phase could have been clamped here, but the 60 degree clamp PWM is not really clamping like that. So, if I were to draw the energy loss here, if I were to draw the energy loss, so this might be 0 here, this would be 0, this is the current waveform, it follows here and it goes higher. So, you can see that it is not quite, there is a reduction, but the reduction is not exactly at the middle. So, the reduction in the energy lost is lower than what it was for the 0 degree power factor angle case. So, what should you actually do? It is best that you clamp it around this. Where is it coming? Now 120 degrees is where the peak is occurring. Better clamp the phase between 90 to 150 degree, which is what you are doing here, clamping it from 90 to 150. With this PWM method, you will get the same advantage to the same extent that you got with 60 degree clamp PWM at unity power factor. So, what you have done? You are clamping between 90 to 150 degree when the phase current is at the peak is here. So, the next slide I have shown this is for the leading power factor and that is the lagging power factor. So, if it is like here, so this is about 90 to 150 degree, you are going to clamp it around this now. So, if let us say it is not 30 degree lag, the phase is lagging, current is lagging by 20 degree lag. So, what you can actually do is you can clamp from 80 degree to 140 degrees. So, from up to 0 to 30 degree possible, you can actually shift your clamping position, so that you can get your 50% reduction in the energy lost. If you are talking of a reduction in power switching loss, if you are talking of the same frequency, and 33% reduction if you are talking of an increased switching frequency of 1.5 times. So, this is what is possible now. This is for 30 degree lagging power factor case. If you are talking of 30 degree leading power factor case, sometimes the load could be leading power factor. In that case, this is helpful. So, if the load current is 30 degree leading power factor, then this would actually result in the best possible reduction that is possible with this now. So, we are looking at everything in terms of the modulating signals right now. After a while, we will go into the space vector domain and we will do it a little differently. Alright. So, now let us say you come to the 0 power factor, we are looking at very specific examples. For example, we are looking at unity power factor, we are looking at 30 degrees and we are looking at 90 degrees kind of power factor angles, so that we are developing some idea. Now, let us say it is 0 power factor. So, the current is actually crossing 0 when the voltage is at its peak and the phase is clamped here. So, it is useless. I mean, the amount of energy that you are going to save, anyway, even if you had switched the phase, the current going through 0, the energy loss is very low. So, you do not need to do this now. If you look at the energy loss, how is the energy loss? It is saved here, otherwise the energy loss follows here. So, here also the energy loss is 0, the energy loss follows like this. So, you can see that the energy loss is quite high. You are not clamping the phase when the current through the phase or the energy switching energy loss is high. So, this is not the right thing to do. So, it will result in very small reduction in your switching loss when you average it over a cycle. In fact, if you consider this is only if you consider the same carrier frequency. If you consider the carrier frequency to be 1.5 times, then you will see that 60 degree clamp PWM actually results in higher switching loss, than conventional space vector PWM at 0 power factor. So, this is a very good solution when it is at unity power factor, but this is not a good solution when you are really talking of 0 power factor. You need to go do it differently. So, let us say 0 power factor, what happens? The trouble with this low power factor is when the current is having its peak, the voltage is close to 0 and the phase cannot be clamped. So, the current phase carrying the highest current cannot be clamped, but you should be able to clamp the phase carrying the second highest current, which is what is achieved by split clamp PWM. For the same example, let us say you take 30° clamp PWM. Now, what this 30° clamp PWM does is, it clamps here, like from 120 to 150° the R phase is clamped. So, it is 0 power factor load. So, you will see that here it is 0 crossing, at 120° it will be 0.5 times the peak value, here it will be 0.866 times the peak value. So, it will actually be clamping the current when the current value is between 0.5 times its peak and 0.866 times its peak. So, I have shown it more clearly here. So, this is for example is the R phase modulating signal for a 30° clamp PWM. Now, it is the R phase modulating signal. This is the common mode component for the 30° clamp PWM. You add that, then you get your R phase signal like this. Now, what you are doing? This is your R phase fundamental current. You can see that it is switched here when the current is between 0 to 30°. It is fine. You cannot clamp it when it is close to its peak, because the voltage is close to 0. So, you are doing the best thing, you are clamping this phase when the current is between 0.5 times the peak to 0.866 times the peak. Let me draw this energy loss. So, if I draw the energy loss, here it follows the current up to what point? Up to this point, then it is 0, then up to here it is 0, then here it goes. So, here this is 1/2 cycle of the energy loss, this is 1/2 cycle of the energy loss. So, you see that it starts increasing this side again. From here to here, if you see, you cannot clamp close to the peak. So, you are clamping it between, if you call this as 0, you are clamping between 30 to 60° and 120 to 150°. You cannot, ideally you want to clamp between 60 to 120, it is not possible at all. So, you are doing this now. So, this 30° clamp PWM is a particular example of split clamp PWM. So, this clamping duration and that clamping duration add to 60°. It is 30 and 30 here, it need not have to be, it can be 10 and 50 here, or it can be 50 and 10 here for example. So, that is what we call as split clamp PWM. Now, we will generalize this. Now, this is continuous clamp PWM. So, what you do? You can clamp a phase for 60° continuously. So, to a particular bus, here again the same phase is clamped to the other bus for 60° continually, therefore, you call it continual clamp PWM. So, this is oriented towards lagging power factor loads. So, I am calling it as continual clamp PWM 1. This is oriented towards leading power factor loads, I am calling it as continual clamp PWM 2. So, then we have split clamp PWM. So, here we have the split clamp, right. So, here you have this is low and this is high, like say 10°, I mean this is 50°. The other example is this is 50 and this can be 10, we call this split clamp PWM 2. So, this continual clamp PWM and split clamp PWM together represent the complete range of bus clamping PWM methods except 120° clamp. So, these are the PWM methods which can ensure that all the 6 devices, the converter operates in a balanced fashion. So, this actually summarizes everything. Okay. Now, let us look at the same thing from the space vector point of view. How do we represent? So, this is the space vector domain, reference vector is rotating, you have a particular sample. Now, that sample is obtained by time averaging of this vector and that vector. Now, we are calculating all the dwell times like this. We have discussed this I mean many times when we did the space vector based PWM module and the subsequent line current triple modules. So, we are going to apply the vector states like 0, 1, 2, 7, 2, 7, 2, 1, 0 like this when you have space vector PWM. The active vectors are applied for t1, t2 seconds. The null vector is applied for tz by 2 and tz by 2 here if it is conventional space vector, or it can be some other ratio for the other continuous PWM methods, and the duty ratios are actually given by this now. If it is bus clamping PWM method, what do? You apply, let us say, only 0 for the entire duration tz, or 0, 1, 2, 2, 1, 0. So, this is one way of doing bus clamping PWM. This is the other way of doing bus clamping PWM. You apply only the 0 state 7, the entire tz you apply the 0 state 7. So, 0 never gets applied. In this case, R phase gets clamped. In the previous case, the B phase was getting clamped to the negative bus. Here, R phase is getting clamped to the positive bus. So, these are the only two possible switching sequences that are bus clamping sequences in sector 1. So, you have to only either apply one sequence or the other. So, what you do is, let us say sector 1, you divide that arbitrarily by some angle gamma. Gamma can vary anywhere between 0 to 60 degree. Between 0 to gamma, let us say you apply 7 to 1, 1 to 7 sequences. Between gamma to 60 minus gamma, you apply 0, 1 to 2, 1, 0 sequences. This is one possibility. You can apply the similar sequences in other places. For example, 7 to 1 is similar to 0, 3, 2. So, 7 to 1 in sector 1, 0, 3, 2 in sector 2. You can apply similar sequences everywhere now. If you apply these sequences, what really happens is, you can see that R phase is clamped over this duration. You can see that R phase is clamped over this duration, and similarly you will also find that R phase is clamped, but to the negative bus during this duration. So, this is same as your continual clamp PWM method. Similarly, you will find for the other phases now. Let us say this is the other option. So, you are using 0, 1, 2 in the first portion of sector 1 and 7 to 1 in the next portion of sector 1. So, if you look at this, what you will find is, you will find that R phase is clamped to the positive bus in this duration, and again you will find that R phase is clamped to the positive bus in this duration. So, R phase is clamped for a total of 60 degrees, but it is divided here. This is for a duration gamma and this is for a duration 60 minus gamma in these two, it is divided like that. Similarly, you will also find that R phase is clamped to the negative bus opposite here. This will be R clamped to the R phase would be clamped to the negative bus, here also R phase is clamped to the negative bus. So, this is split clamp PWM represented in the space vector domain. So, this is continual clamp PWM, this is split clamp PWM, this is how they are representing. Between them, together they represent all the discontinuous PWM methods except like 120 degree clamp PWM, which are asymmetric anyway. Now, if you want to compare two sequences, you can only apply 0, 1, 2 or 2, 7 or 7 to 1, those are the two sequences. Basically, how do you compare? You compare them based on the energy lost. How is the energy lost? The total energy lost in a subcycle with 0, 1, 2 and 7 to 1. How much is the energy lost here? I am talking of normalized energy lost. So, this E012 is actually given by the unsigned value of IR plus IY, and this loss, if you are applying 7 to 1, you are switching Y phase and B phase, you are not switching R phase. So, the loss is given by the unsigned value of IY plus unsigned value of IB. Now, what is unsigned value of IR? It is sine of omega t plus phi. I am taking this phi as the power factor angle. If phi is negative, you can call it lagging power factor. If phi is positive, you can call it as leading power factor. All right. So, this is IR, this is IY. The power factor angle is phi, and this is IY, this is IB. I have written this. So, I have written the same thing as sinusoidal functions. So, what is this omega t? I am considering sector 1. So, sector 1 starts from where the R phase is having a positive peak. Omega t is equal to 0 at the positive 0 crossing of R. Sector 1 starts where R is having a positive peak. So, omega t equals 90 degrees where R phase starts, and it is 90 plus alpha. Omega t can be represented as 90 plus alpha. Sector 1 extends from 90 degree to 150 degree. So, this is 90 plus alpha, where alpha range is 0 to 60 degree. I have not indicated that, but you can certainly understand the range of alpha is 0 to 60 degree. So, you can write this expression now. So, you have an equation. If you solve this equation, you will get a relationship between alpha and phi, for which the energy the losses are equal. You can get the condition E012 less than E721, or you can get the condition E012 greater than E721. So, you will know for what values of alpha and phi, or for a particular value of phi, what ranges of alpha 012 is better and 721 is better. This is one way of doing. This is the basis by which you can arrive at a particular PWM method, which will result in the lowest switching loss at a particular this is discontinuous PWM method for a particular power factor angle. So, this can help you this. So, you can compare these two sequences now. So, you can actually represent it like this. What you are trying to do is, let us say you can consider a particular box. Now, here this is the power factor angle, phi is equal to 0 degree, phi is equal to 90 degree, phi is equal to minus 90 degree. So, one side it is leading, the other side it is lagging. So, you can try and see if it is generally, if it is for lagging power factor, you will find that 7 to 1 is better, and this is for alpha. This side you can start from alpha is 0 and alpha is 60 degree. So, you can plot on this plane, you will generally find that 7 to 1 is better and 0 1 2 is better on the leading power factor sides, and actually for phi is equal to 0 and alpha is equal to 30, both are equal. Similarly, you will find that both are equal here. you will actually get a line if you solve the previous one. You solve the previous one, this equation. I am not going to do this, you can just take this as a home exercise. You solve this, you will get the lines that will divide this into two regions. One region of superior performance of 0 1 2 and the other region will be superior performance for 7 to 1. That is, you will set certain combinations of alpha and phi for which 0 1 2 leads to lower loss than 7 to 1 and vice versa. So, this combination, if you do that, it has also already been worked out in the literature. I will give you the reference also shortly. So, you can actually find out, you will come up with the most optimal combination of 0 1 2 and 7 to 1, that would give you the optimal PWM method, optimal discontinuous PWM method for minimizing switching loss at a particular power factor angle. So, I am leaving this exercise for you. Similar exercise can be carried out for all the other sequences. So, this is advanced bus clamping PWM. You are just doing 0 1 2 1, 1 is being applied 2 times for 0.51 seconds each. Here what are you doing? 7 2 1 2. So, 2 is being applied for 0.52 times each. So, these are advanced bus clamping PWM sequences. R phase is clamped, B switches once, but Y switches twice. As I told you, this will be advantageous if the energy that you have saved by not switching R phase is greater than the energy that you are losing by switching the Y phase, or in other words, if the R phase current is greater than Y phase current, this is an advantageous, otherwise this is disadvantageous. So, you should know where to use it. So, that is what we are trying. So, 0 1 2 1, I am just trying to represent it here, 0 1 2 1, 1 2 1 0. Similarly, 7 2 1 2, I am sorry, 2 1 2 7, this is the other sequence for advanced bus clamping, and this is 1 0 1 2. You start from 1, go to 0, come back to 1 and go to 2. Similarly, 2 1 0 1, these are sequences. This is yet another bus clamping PWM sequence 2 7 2 1. 7 or 1 2 7 2. So, you start from 2 7 2 1 1 2 7 2. So, these are advanced bus clamping sequences. So, you have 4 of these sequences which we can call 0 1 2 1, 7 2 1 2, 1 0 1 2 and 2 7 2 1. Let us take 2 of them, 0 1 2 1 and 7 2 1 2, we can compare them easily. What happens? 0 1 2 1, R phase switches once. So, the energy loss is given by IR plus 2 times IY, because Y phase switches twice, IB does not switch. If you take E 7 2 1 2, Y phase switches twice. So, this is proportional to 2 times unsigned value of IY plus IB, here R phase does not switch. So, you know the expressions for IR, IY and IB. So, you can put in those expressions, and this is, we are looking at sector 1, therefore, omega t is equal to 90 plus alpha. You actually get an equation in terms of alpha and phi. There could be multiple solutions, please be careful about that, there could be multiple solutions, and so along for this particular relationship between alpha and phi, you will have 0 1 2 1 equal to 7 2 1 2, their losses will be equal. You can easily find the condition E 0 1 2 1 greater than E 7 2 1 2 and E 0 1 2 1 less than E 7 2 1 2. So, that would be a way to combine 0 1 2 1 and 7 2 1 2 to come up with a PWM method which is got a lower switching loss than 0 1 2 1 individually and 7 2 1 2 individually. The same thing you can do, you like what I said before, you go ahead and just plot it. You take a box, this is phi 0 degree, minus 90, plus 90, and this is alpha 0 degree, 60 degree. You try to do this now. You will see that both of them are equal at this point. This is one point, these are some points I am giving you straight away, they will fall on certain lines. You find out those points. Anyway, they are there in the references that I am going to give you also. Similar exercise can also be done for E 1 0 1 2, except that now R phase switches twice. So, it is 2 times IR plus IY. 2 7 2 1, B phase switches twice. So, it is 2 IB plus IY. You can do a comparison, this will tell you when 1 0 1 2 is better than 2 7 2 1 or vice versa, and then you can use an appropriate combination of 1 0 1 2 and 2 7 2 1, which will give you lower switching loss than these two sequences put together. The same way, so this exercise can actually be summarized similarly on the alpha 1 versus alpha 2 plane. You can once again summarize it on the alpha versus phi plane as we have done before. So, it is not necessary that you have to compare only the two sequences with two of them, you can compare all the sequences with each other, and that is what will give you something called as minimum switching loss PWM. The name that you find here as minimum switching loss PWM, that is actually discussed in this particular paper. So, the alpha versus phi planes that I told you, and whatever you could actually say, these are all actually discussed here. So, you can do this as a homework and you can verify your solutions with what has actually been given in this particular paper. So, this actually tells you how to derive a minimum switching loss PWM, which is a combination of all these sequences, 4 advanced bus clamping sequence and conventional sequence and the 2 bus clamping sequences. Using these 7 sequences, there is a particular PWM method which minimizes the switching loss at a given average switching frequency. So, it is shown that this is an advanced bus clamping PWM method. So, it is shown that the advanced bus clamping PWM sequences are better than the other sequences when you are looking at reducing switching loss at a particular average switching frequency. So, the details are available here, you could actually look at it now. So, this is deals with the minimum switching loss PWM for the entire range of power factor. Here it is dealt with for a particular power factor, this is reactive power compensator. So, which is actually you are looking at 90 degrees, that is STATCOM is going to supply power, reactive power. So, at it in the current is leading by 90 degrees. So, this would be a one particular PWM method, and for this particular PWM method it is shown that the power conversion loss is lower. I mean, of course, minimum switching loss is going to reduce the switching energy lost. So, you know, we did this simplified analysis. The simplified analysis would say that there is a certain amount of reduction. There is a variation between the simplified analysis and the actual analysis. So, this paper shows that there is some difference between the two, but nevertheless with the minimum switching loss PWM, there is certain good amount of reduction in the switching loss. So, for example, here this our simplified analysis predicts some 22% reduction in switching loss, but the actual reduction in switching loss found for a actual power converter, when you do the calculations in detail, we are getting it to be something like 15%. And there is conduction loss also. If you look at the total power conversion loss, this paper reports that there is some 7 to 8% reduction in the total power conversion loss. That is what it reports, and this is for a specific application of reactive power compensation. So, where you have these power losses evaluated at this thing. Here also you have analysis and you have the experimental results, you know, which are shown at some power level of few kVA. Here it is shown at a power level like 100 to 150 kVA power level, this is shown here. So, these are two papers which are directly concerned with minimum switching loss PWM. This is actually combination of advanced bus clamping PWM sequences which minimizes the switching loss at a given power factor. That is what we would say as minimum switching loss PWM. So, there are these other references. This is a classical reference and there are quite a few number of other papers. This actually discuss about the influence of the modulation method. These are the continuous and discontinuous modulation methods on the conduction and switching loss. I mentioned this even in my last lecture, and you know, some calculation how to, you know, the calculation of conduction and switching loss for continuous PWM and some discontinuous PWM and advanced bus clamping PWM have been done as part of this thesis. So, this is again a particular reference, and here this is one which shows the advanced bus clamping PWM, some specific advanced bus clamping PWM which uses 0121 and 7212. They actually give you a lower switching loss at high power factors. So, this talks of some specific PWM method. So, these are actually useful references. So, I mean, I would I hope that, you know, thank you for your attention up to this point, and I hope that this lecture was useful to you, and you could actually look through these references which will give you good information on how to design PWM methods that would reduce switching loss and total power conversion loss. So, PWM methods are very useful in reducing the switching loss and thereby increasing your efficiency of power conversion. So, I thank you very much for your interest in that. I hope that this lecture and this module both were useful to you, and I hope that the lectures were all useful up to this point of time, and I hope that you will have sustained interest in following the next 3 modules which are yet to come. Thank you very much for your interest.